Okay, so let's do a problem involving finding an approximate area under a specific curve using both an upper sum and a lower sum. Take two. Okay, so let's do an example where we find the approximate area under a curve on a given interval using an upper sum and a lower sum. Uh, we're going to do it separately, once using an upper sum and once using a lower sum. And I've specified that we're going to use n equals 3, so we're going to use three subintervals or three rectangles as we do this. So, all right, the first thing to observe is that the interval is the interval negative 1, 2, and the length of that interval, we can put it in, the length is equal to 3. That's convenient because we've chosen n equals 3 as the number of subintervals. So when we divide the larger interval into subintervals, we're just going to get that's 0 and then 1 and 2. We have three subintervals, each of them having a length of 1. That's okay, and that makes it convenient. That means the width of each rectangle is actually going to be 1, which will make it fairly convenient to calculate the areas of those rectangles. All right, so for the upper sum, let's do the upper sum. We want to choose the highest point in each subinterval. What we can see is that, actually, let's give the subintervals, let's write them out. So the subintervals are negative 1 to 0, 0 to 1, and 1 to 2. So we can see that the highest point in the subinterval negative 1 to 0 is that dot. In other words, right over x equals 0. Just based on what we know about the graph of y equals 5 minus x squared, it has a vertex at x equals 0. That's where its max is. So, okay, so we know that the highest point in the first subinterval is at x equals 0. We can also see that if we look at the second subinterval, because the function is no longer increasing, see it's increasing in the first subinterval, so its highest point occurs at the right endpoint of the first subinterval, but then it starts decreasing, as we know from the previous chapter. That's what happens when you hit a maximum. You increase to the left and then you decrease to the right. So we can see that therefore the highest point in the second subinterval is also that red dot. We can see that the highest point in the third subinterval is going to be here because the function continues to decrease, so the highest point is at x equals 1. So let's put the location of the max. That's going to be x equals 0, x equals 0, and x equals 1. So we can see that the rectangles that we're actually going to draw are like that. So that's going to be like that. Try to draw different types of hash marks for these. There we go. So that's what the three rectangles are, and you can see that actually the height of the first and second rectangles are the same. So let's also put here the area of each rectangle. I'll just write this symbolically like that, area of rectangle. So the area of the first rectangle is, we know that it has a width of 1, so it's 1 times the height at x equals 0. The function is 5 minus x squared, so when I plug in 0 for x, I just get 5. So I'm just going to put this in like I did the first time. This is the width, and this is the height of the rectangle. So the area of the second rectangle is going to be 1, because they're all of width 1, and also times 5, because we've chosen, once again, the maximum at x equals 0, and it's going to be the same y value. And at x equals 1, that's going to be y equals 5 minus 1 squared, which comes out to 4. So that will give us a width of 1 times a height of 4. So we can see that the area under the curve on the given interval, negative 1, 2, I don't want to keep writing that, is going to be approximately equal to 1 times 5 plus 1 times 5 plus 1 times 4, which is equal to 5 and 5 and 4 is 14. And by the way, I'm correctly using the approximate equals and the exact equals. In other words, I'm saying the area under the curve is approximately equal to this sum of three products, which is exactly equal to 14. So that's why I'm not asserting that the area under the curve is exactly equal to 14. I'm just saying that 14 is exactly equal to the approximation I've written out. So okay, so that's the upper sum. let's do the same problem with the lower sum. So let's just draw the function again. Okay, so for the lower sum, what we want to do is we want to choose the lowest value in each subintervals. We have the same subintervals. So we can see that the location of the min is the min in the first subinterval is going to be here because the function is increasing on this first subinterval. And we can also see that the location of the location of the min on the second subinterval is going to be here because the function is decreasing on the second subinterval, so it's at the right endpoint. And we can see that for the third subinterval, the min is there. So that's going to give us x equals -1, x equals 1, and x equals 2. So plugging in these values, we'll see that the height of the rectangle, let me just put in what these rectangles are. There's that one, and there's that one. And this is going to be those hash marks, these hash marks, and these. So we can see is that the height of the first rectangle is going to be, write the function again, y equals 5 minus x squared. When I plug in -1, I get 5 minus -1 squared, which is 4. So that gives me 1 times 4. Again, the width of each subinterval is still going to be 1. And then when I plug in 1, I also get 4. 5 minus 1 squared is 4. And when I plug in 2, I get 1 times 5 minus 2 squared is 5 minus 4, or 1. So that means that the area under the curve is approximately equal to 1 times 4 plus 1 times 4 plus 1 times 1, which is equal to 4 plus 4 plus 1, or 9. So this is the upper sum with n equals 3, and this is the lower sum with n equals 3. And I have to specify, by the way, that n equals 3 like I did in the problem, because of course if I had chosen a different number of subintervals, then the endpoints on each subinterval would be different from what you see here, and the analysis of where the min or max is on each of those different subintervals would be different. So it's important to note, exactly how we've divided up the given interval. But this is just an example of how to find an upper and a lower sum in a situation where it doesn't uniformly come out to the right or left endpoint for every single subinterval. As you can see here, in the first example with the upper sum, it was the right endpoint of the first subinterval, the left endpoint of the second and third subintervals. For the lower sum, it came out to the left endpoint of the first subinterval and the right endpoint of the second and third subintervals. So that's the upper and lower sum example.